Hello everyone, I'm Jessie Yan. I'm an assistant professor in the Department of IOE. Today I'm going to introduce you the range of research we conduct in the area of human systems integration. We have one of the best human factors ergonomics program in the nation. Human factors is concerned with the application of what we know about people, their abilities, characteristics, and limitations to the design of equipment they use, environments in which they function, and jobs they perform. Our ultimate goal is to optimize human performance. We have 13 faculty members doing research covering both the cognitive and the physical side of human factors. Let's see the range of projects we do here in human systems integration.
So the work that we do as ergonomists affects a wide range of different environments, some of which may be aviation, it may be the operating room in a hospital, it may be the car that you're driving. All of these things require effective design of information, and they require effective design of controls to ensure also that you don't develop physical problems and you are supported in doing the cognitive work. We're trying to make it safe, we're trying to make it efficient, we're trying to make it enjoyable. And that's really what ergonomics is about.
Next, I'm going to showcase some of the existing projects we have in IOE. The first project I'm going to introduce is Attention Management in Aircraft, led by Professor Nadine Sauter. Professor Sauter's group tries to understand how pilots make decisions and manage their attention in off-nominal situations, so once-in-a-lifetime situations. I believe many of you have watched the movie Captain Sully. In the movie, a flock of birds damaged both engines of Captain Sully's aircraft. And in that moment, Captain Sully needed to make life or death decisions within seconds. And in the end, he successfully landed the aircraft on the Hudson River. But why Captain Sully was able to make such a good decision and manage his decision so well in those challenging and stressful situations? This is the question that Professor Sauter's group tries to answer. In order to answer those questions, Professor Sauter recruit pilots and ask them to wear an eye tracker shown in the lower left corner. By using the eye tracker, her team was able to track where the pilots were looking at, shown as the red and orange green dots. The next project I'm going to showcase is led by Professor Tom Armstrong, Models for Assessing Localized Fatigue. I'm sure many of us has experienced localized fatigue, for example, lower back pain in our life. The traditional way of assessing localized fatigue, assessing lower back pain, is through observation. So the company can hire a human factors engineer or ergonomist to conduct the observation. And the engineer could assess the risk of the worker getting lower back pain. This method is convenient, but it is very time-consuming and costly. So Professor Tom Armstrong has and his students developed model-based analysis to assessing localized fatigue. Let's see what he says about it.
The job or from observing video recordings of the job. This information may be supplemented with physical measurements as well as the use of instrumentation. The net result is that we gather information about force and postures that can be inputted into various exposure indices such as the ACGH TLVs RULA or REBA, the strain index, OKRA, or others to assess the risk of various musculoskeletal disorders or localized fatigue. Alternatively, with model-based analysis, we don't necessarily even look at the job. We start with descriptive information about the work goals, the work standards, and specifications. We look at process sheets. We look at material and workspace and material specifications. We may use historical data from similar jobs that have been designed in the past. We may draw on the experience of engineers and supervisors who are familiar with this kind of work. This information is used to determine the dimensions of the workspace, the locations of the work objects, the weight and torques required to operate tools and equipment and to handle materials, the frequencies of various activities. This information in turn is used with computer-aided design tools to describe the spatial relationship between workers and the workplace. It's used with predetermined time systems to describe the temporal patterns of work. It's used with biomechanical analyses to assess the force and moments and postures of the workers. Again, this information is used to describe or develop models of force and posture patterns, which again can be inputted into these various exposure indices to assess risk of various musculoskeletal disorders.
The next project I'm going to showcase is Orbital debris damage detection, led by Professor Leah Sterling. There are more than 20,000 pieces of debris or space junk in the space, and they are traveling at a speed of up to 17,000 miles per hour. At this speed, any collision with those junk with the debris can damage spacecraft or space station. Currently, inspection of the station is performed primarily by astronauts through extravehicular activities. These efforts are costly, subject astronauts to more risk, and requires a great deal of oversight from mission control. So in this particular project, Professor Sterling and her group develops a new approach. Instead of sending astronauts out of the space station, they are sending a group of small satellites out of the space station to do the inspection work. So the astronaut or the human operator will still be inside the station. And the questions they want to understand is, how can humans and small satellites work together to perform inspection tasks together? How this task should those inspection tasks be synchronous or asynchronous? How should spatial information be displayed to the astronauts or human operators? Here you can see they are using VR to develop different displays to facilitate the human autonomy teaming, to facilitate the interaction between the humans and small satellites. The last project I'm going to showcase is Takeover Transitions in Level 3 automation. I'm sure many of you have heard of Tesla. If we look at the level of automation, so how autonomous Tesla is only at level 2 automation. That means even though Tesla can do lane keeping, object detection, and other functions, the ultimate driving responsibility still lies within the human. So that is level 2 automation, Tesla. If we move one level up, become more autonomous, we have level 3 automation. So in level 3 automation, the vehicle can perform all the driving functions most of the time autonomously. However, when the vehicle reaches its system limit, it will require the human driver to take over the driving task within seconds. As you can imagine that this takeover transition is a very challenging task. In this project, we want to predict whether a human driver will be able to take over successfully by analyzing their physiological data. We collect the human driver's physiological data, for example, their eye tracking data and their skin conductance data. By analyzing the patterns of those physiological data, we will be able to predict whether they can perform a takeover transition successfully.
Automated mode engaged.
And this video shows you the different types of physiological data we've collected in the study. By analyzing the patterns, we will be able to predict the human performance. Besides research, we have a strong continuing education program here.
The goal of the continuing education program is to provide workplace health and safety information to those who can affect workplace safety and human performance. This is done through two ways. First, through on-site live courses, and the second is through our YouTube channel that contains a large database of workplace analysis videos. The information taught in these courses is used to evaluate workplaces and products in order to maximize workplace safety and human performance.
At last, let's see a testimony from one of our former PhD students, Dr. Brandon Pitts. Dr. Pitts is now an assistant professor at Purdue University.
I can tell you that my time here has been amazing. The focus, in my opinion, was not so much on exams, but it was on projects, on developing relationships with my classmates, learning how to collaborate with them. One of the things that I've admired the most about the Center for Ergonomics is the connection and the resources. And just to have the expertise, anything that you're looking to do, if you need help with data analysis, if you need some type of statistical software package, you have faculty members who are doing things that involve, for example, human-robot interaction, all the way down to how do I redesign an assembly process from more of a physical ergonomic standpoint. Any question I had about any topic, generally there was someone here who could help answer that question.